Hello, hello.
going through various stages. Then we'll look at some wireless problem statements which we could solve with AI and get some hands-on examples. All right. I'll also share a bunch of resources and then we'll have an interactive discussion at the end and we could see going through various stages. If we just look at wireless evolution of communication systems over time, like so I think since all of you might be from the wireless background, So let me ask the other question. So let me ask the opposite one. So who here has not done a machine learning course, or who here is very new to machine learning? If you could just raise your hand, and we could go ahead. Yeah, great. I think a lot more people have not done a machine learning course rather than. So let me ask the opposite one. So here has not. So we'll go over some very brief basics of machine learning. Again, you don't need to. We'll cover these at a very high level. We'll not get into the mathematics of it. I think a lot. So the idea is to give you give you an idea. The idea is to give you an intuitive understanding of machine learning rather than get into the details. Okay, and we'll leave you with resources which you can go and use to sort of learn yourself and work on this. Okay. So so machine learning isn't really as new like AI. It has been there from the advent of computers themselves. So with like it has been popular since the 1950s itself. Machine learning as is a subset of AI. Essentially, it refers to a bunch of statistical methods which can enable machines to learn tasks from data without explicitly being programmed. Right? And these have been again available since the 1980s. Neural networks again came up around again this time as well. But it's only in the 2010s that neural networks and large neural networks really became popular, and they are what is known as deep learning. So essentially, neural networks with multiple layers, which can learn tasks directly from the data itself. So it's only like still very nascent a field, and we still have to see a lot of these being put into action. There's a lot of machine learning, like it's a lot of we hear a lot about machine learning, but very little of it is actually out in the real world. So because people essentially train a bunch of machine learning models, but seeing it through to implementation is what is important. And we'll talk about how you can go through all of these. So let's look at a very broad understanding of what machine learning and deep learning is. So machine learning can be essentially divided up into supervised and unsupervised learning. So unsupervised learning is when you are provided a bunch of data or and you're just asked to classify it. So what you can then end up doing is looking at groups which are similar or groups which are dissimilar, right? So like in this case, suppose I give you some values for features. Features can be any characteristics that we are measuring, and I ask you to group them. So you will end up, if we end up looking at just the feature values itself, you will end up grouping some together because they are close by, and grouping others in a separate group because they're further away and so on. Right? So, and a simple example can be looking at something like say you're looking at something like say these features can be anything from if I give you an example of just measurements from a human being. So maybe weight is a feature and height is another feature, right? So maybe weight and glucose level are another feature, and so on. So if we look at these features, we may end up having groups of something like um, uh, areas where some weight height pairs for something like athletes versus normal people, right? So there might be sort of a difference there, right? Because athletes, so their weight to height ratios and everything might be very different than what a regular person's might. So you would look at clustering these automatically without being given any information about who is an athlete or who is a regular person. The other bit is looking at the other type of machine learning algorithms is supervised learning. So wherein essentially you're looking at uh, two major sets of problems. So classification and regression. So classification, as the name suggests, is you're grouping things into different classes. And regression is you're estimating values, right? You're estimating a numerical value. So deep learning very often is a sort of supervised learning problem because it requires a bunch of like labeled data. The only difference is in machine learning, typically you would need features to be extracted, while deep learning very often doesn't involve a feature extraction step. So we would need very specific features to be extracted for machine learning algorithms, while deep learning is essentially end-to-end learning, where we can simply give in data and then go ahead and uh, map it to certain classes or certain values. Yeah. So if you look at, say, machine learning versus deep learning in action, so say the problem was sort of identifying what sort of uh, vehicle there is in a particular picture, right? So when given a set of pictures, if we are looking at a machine learning approach, what we might do is we might extract features like edges in the boundary and so on, or say the number of round objects in the image or things like that, and then give it to a machine learning model to classify. Whereas if you look at so here, what we would want to specify is the sort of features we want to extract, as well as the type of model that we want to build. Whether we want a linear model which separates out these feature values or so. Whereas in deep learning, we essentially combine these steps together. Okay, in that we give data to a deep neural network, and it just churns out classifications. Okay, so there is no explicit feature extraction step here. The deep neural network itself can extract features, okay? And also learn how to classify them. So what is important is in this case, what we as designers specify is essentially the type of deep neural network. So in many cases, it can be a convolutional neural network, or the CNN, or in other cases, it might be a deep neural network, it might be other types of neural networks like recurrent neural networks. So we essentially need to specify only the architecture of the model. Again, deep learning and machine learning can work with a bunch of different data types. So images, signals, numeric data types, or text, and we'll look at some of these. Now, any questions on this aspect? Machine learning, deep learning, supervised or unsupervised learning. Let's maybe at a very high level. If there are any questions, please feel free to ask away. Yeah. Is this clear to people? So,
Sir, result-wise, in machine learning and deep learning, machine learning, the result-wise, is there a difference in, I mean, a lot of difference, just the accuracy-wise difference. Like say the car that you had shown. So is it that the deep machine learning will identify it as a car and deep learning will identify it as the brand also? Which car? Is it like that?
no, not really. So again, the sort of categories which we want to classify it into are similar. The difference mainly is this feature extraction step, because this is very subjective, right? So if so when training a machine learning model, what sort of features you extract might be very subjective. Uh, so while here there is no explicit feature extraction, so this network is sort of uh, extracting features itself. Having said that, in some cases, deep learning has provided a, a lot better accuracy in comparison to machine learning models for some sort of problems. Simply because like so machine learning models aren't really machine learning models are good for a lot of things, but when the problem is too complex, I think or use cases are very close by, I think deep learning performs a bit better. So there are use cases where you will use machine learning. There are use cases where I think deep learning would be appropriate.
So some cases can be solved using only deep learning.
Yes, I would say there are some cases where I think only deep learning would be a deep learning approach works, because the categories are so close by, like what you were saying, right? If I had to identify different car models itself from different manufacturers, maybe the categories will be so close by that we can't really identify these using a typical machine learning approach. Yeah, so similar. Yeah, yeah. Any other questions? None? Okay. So we'll hopefully this will be a bit more clear once we go along. But please feel free to sort of look at where we can start. So if you look at where you can apply, so now we talked about various types of learning, like machine learning, deep learning. Reinforcement learning is again, we'll talk a bit about it. But if you look at where we can, what sort of wireless problems we can apply this to. If you look at unsupervised learning, right? So maybe small cell clustering is a problem that you can apply it to, or device to device clustering, or detecting anomalies or intrusions. If you look at supervised learning, on the other hand, we could look at problems like channel estimation, user location estimation, spectrum sensing, beam selection, and so on. And then again, on the reinforcement learning side, you could look at something like resource allocation problems, or look at again beam steering and some beam selection problems here as well. Okay. Yeah. I hope this is clear. Are there any other questions? Because now we'll get into the AI part itself, and then we'll go over some examples. Any questions? Yeah. No. Sure. So let's go ahead and look at AI-driven system design. Like if you had to look at looking at applying AI to solve machine learning problems, then how do you break down that problem and how do you proceed? So I'll just describe these 4 major steps, and then you can go ahead and look at applying these 4 steps to your problem, and then sort of structure your work that way. Okay. So so for any AI-driven system design, you would look at initially data preparation first. In this case, you would essentially look at something like either generating data from simulations. So here I'm talking about mainly wireless communication problems. So you would look at generating a lot of data, like so via simulations itself. You wouldn't typically use recorded data for doing this, simply because it is prohibitive to keep recording data, especially in the wireless communication space, right? You would use a lot of simulation generated data for creating the base of it. Is this part clear? I think most of you as wireless communications folks might have already, you would typically do this, right? You would typically write a simulation model for how like SNR varies when users move in an environment, right? I hope this part of it, where simulation comes in to generate data, is fairly clear. Any questions on this bit? Like any questions on why use simulation generated data or why use measurements? Done. The next bit comes in sort of AI modeling itself. So essentially we identify what sort of model might work. How do you work with different neural networks? How do you train neural networks itself? And then look at simulation and testing. So how do you integrate this existing model with the net within the system, and look at doing system level simulation, and finally looking at deployment. So once you have simulated it and it works at the system level, how do we deploy it? Either onto an embedded device like a mobile device, or onto edge devices, or on enterprise systems. Okay. In one case, these 4 steps for a wireless problem can be. Let me just take an example. So in the first data preparation step, we would essentially look at creating a simulation to generate data. So this can be, say, we have generated a 5G compliant waveform, and we are transmitting it from a transmitter array, and the waveform, the signal is being transmitted through a channel. So we are applying channel effects to it. And at the receiver side, we are again receiving a signal which has been affected during this transmission itself. So we have generated some, so we know what we transmitted and we know what we received, and say the AI's objective is to model the channel itself. We need to do some sort of channel estimation. So how can we do that? So by simulation, we control what exactly is the channel effect, what are effects that the channel has introduced. So we know what we are looking to model. In the AI modeling step, we'll come up with a deep neural network to sort of identify, do this channel estimation for us. In the simulation and test state, suppose we have trained a deep neural network to do the channel estimation. Now, does that really work when transmitting this data? So now we repeat the same simulation, but instead of using regular modes to, at the receiver side, we would look at replacing the channel estimation block with this deep learning block. Okay. And finally, if that works, we would typically look at deploying it onto, say, an edge device or onto some hardware, typically, say, an FPGA or an SoC. Right? So that is how you would look at all these 4 steps. So is that fairly clear to everyone? Any questions at this point before we jump into the example itself? So any questions on any of these 4? So you're muted if anyone wants to speak. None? Okay. Let's go ahead. So very often you know that you can't really do this with you can't really get the answer in the first shot. So the objective will be to iterate through these very quickly, and that is where MATLAB comes in. Okay. So one thing. So on the first side, on the first step, let's look at that. Your data preparation and simulation generated data. So in this case, you can either acquire data directly into MATLAB using a bunch of equipment. There are support packages available for directly integrating, directly taking in data from very low cost devices like an RTL SDR or a Pluto SDR, or you could interface with USRPs from NI, and you could also look at connecting to various RF or spectrum analyzers or RF signal generators and control them directly via MATLAB. So another bit that you can do here is look at generating different waveforms from MATLAB itself. So let me just go ahead and do that. And in case you are logged on to your devices, you could go ahead and explore these yourself as well. Okay, but for now, just observe what I'm doing, and then you can go ahead and see if I'll give you maybe a few minutes to go over these and see that for yourself. Okay. So if I open up the MATLAB interface, so I have one open. Okay. So what I would do is so this is my MATLAB interface. So I'm working with the installed version of MATLAB. So if I look into the app section here, and if I look at the drop down, there are a bunch of ready-made apps available. And if I look at the signal processing and communication section over here, so there are a bunch of signal processing and communication apps. So in this case, you can look at the wireless waveform generator app, okay, essentially which can help us generate a bunch of wireless waveforms. So if I do that, if I open that up, I'll just go ahead and wait for that app to open up. So anyone who has used these apps before, the wireless waveform generator? if you could, so anyone who has already used it before? Yes, no, okay. So I'll just wait for this to open up. So yeah. So typically, what you would do when so typically when writing code for simulations, right? You would typically end up generating waveforms yourself by writing code, right? So in case you are so yeah. So typically you would end up writing code for generating these wireless waveforms yourself, right? However, if you're doing a lot of uh, if you are working with any standard compliant waveforms like your 5G or LTE waveforms, then you can utilize this app right away to generate a bunch of these waveforms. So on this wireless waveform generator, you can see I can start a new session, and if you look at the waveform types, so you can generate a bunch of 5G waveforms, LTE waveforms, Wi-Fi, wireless LAN. You could also look at there's with newer Bluetooth standards, you could look at Bluetooth low energy and other waveforms here, or look at introducing custom modulation schemes. Okay. If you're working with any sort of radar waveforms, you could again go ahead and generate those as well. So in this case, if you want to do a very custom OFDM, you could go ahead and look at defining a bunch of parameters here, like what is your FFT length, what is your cyclic prefix, how many symbols do you want to take, and so on and so forth. And you could go ahead and look at simply generating these. Okay. So when you generate them, you could so this will run a simulation in the background and give you the results, right? So this is what your waveform itself looks like, and these are what your symbols look like. Okay. In case you want to introduce impairments in the waveform, you could go ahead and introduce impairments as well. So what sort of impairments do you want to sort of introduce? Do you want to introduce sort of IQ imbalance, phase noise, or any sort of frequency or phase offsets? You could go ahead and introduce those. Okay. So suppose I want to introduce some sort of IQ imbalance, and let me just go ahead and generate again. Okay, and let's look at visualizing this. So, what's the sort of signals itself you are generating, and the spectral view of it, as well as the looking at different subcarriers and so on. Okay. And what is useful to do here is you can look at generating this and exporting all of these outputs to the workspace to work with. You can export this to a file, or you can export it to a MATLAB script. So whatever you did here, you could simply go ahead and generate a simple MATLAB script out of that. And this will go ahead and look at generating this. Okay. So this is just the OFDM signal which was generated. So the idea is the app isn't exhaustive. So there is MATLAB functionality which is not built in the app as well. So, but the idea is to quickly get started with the app and generate a bunch of waveforms. All right. You could do the same thing with a bunch of 5G waveforms as well. You could go ahead and look at a bunch of NR test models, and you could go ahead and generate data for that as well. Okay. So what you can do now is maybe look at opening up. You can see if this app is available at your end, and see if you can generate a bunch of data and see if you can export it to a script. Okay, if you could go ahead and do that, that would be great. Yeah, so let's maybe take 5 minutes to go and do that. Yeah. And so let's just take 5 minutes to go do that. And in the meantime, if there are any questions, please feel free to sort of go ahead and ask as well. So
transmission points at the station.
So yeah. So I hope everyone, if you could maybe get back. So I hope everyone was able to sort of try that out. Uh, so any questions on that aspect of it? Uh, uh, were you able to sort of look at how you could go ahead and generate data? And was that clear? Any questions on that aspect? So is this app useful for generating data for from your, either your research point of view or from your teaching point of view? Maybe if you could answer quickly.
Yes, sir.
Is this useful? Maybe people who
Useful,
Useful, sir.
okay, sure. Great. So one aspect of the app which we did not explore is the aspect about connecting to various wireless uh, uh, connecting to various sort of instruments and then going ahead with acquiring data from there. Okay. So if you look at the second tab, the transmit tab there, you could go ahead and do that as well. So let me just go ahead and just give me a moment.
So there is one question. Sir,
Yes.
just one question. What is the data actually here? That is waveform or that is input data? There are two things in the script generated. There are two variables in the space, workspace.
In the workspace?
Yes. In the workspace, first variable is the data input.
Okay.
The last one is the waveform. So what is actually the data? Actual data input is.
Okay. So what did you utilize? Did you just do a particular OFDM, or what was the waveform type that you selected?
Simply OFDM, what we have gone through now.
Okay, sure. So let me just go ahead and select that itself, and let me just go ahead and generate, and then let me walk you through those. Yeah. So if at any point you're sort of stuck about and wondering what is the sort of data which is generated, you could again simply, you see this help button over here, just click on that, this will open up the documentation, which you can go over and look into details. Okay, so say the first example is app-based OFDM waveform generation. So how you could go ahead and do that, and see if we look at the examples itself. Yeah, okay, there isn't really much here. So let me just export to workspace and let's see. Okay, so this just gives me one variable. So it just gives me one variable VAR, and what it gives is, say, just for me, it's just the sampling as well as the waveform itself. So the real and complex parts here. So nothing else. Is it something similar for you, or is this the same for you as well?
It's a little bit different, sir.
Okay. Sure. But typically, like, yeah.
Sir, how to please would you please show me how to see the documentation from where did we get you get?
Sure. So for any sort of documentation, you will see most windows will have this help button on top. You see this button right at the very top. Let me just zoom this in.
Which version of MATLAB is this?
So the wireless waveform generator app has been there for quite some time. You can maybe utilize this in. So it should be there for at least the 4. So I had shown you that in R 2022P, which is the latest release from September of this year. But the wireless waveform generator should be available for other versions as well. Like, so at least from R 2020 or even before that. So in this case, you can go ahead and so there would be the help button on top here. Yeah, is that clear? How to get to the documentation?
Yes, sir.
Any other questions?
all these four steps, these are to implement in a Simulink, I think. Or we can implement in MATLAB itself.
So you can implement it in MATLAB itself. In some cases, you may want to take it into Simulink and then do that. But again, like mostly it will be.
At last stage, you said about the embedded target. So I think using Simulink we can generate an output. Is it possible using MATLAB?
In Simulink, you can generate what? Sorry, your voice broke up a little.
Yes, for the target, actually, we want to load the data on the target, the embedded system, whatever. So for that, we have to generate autocode. That can be generated using Simulink. Or we can do that using MATLAB also.
You can generate HDL code or you can generate C code using MATLAB also. However, it is not as intuitive. So you can use either, but I would say generate it using yeah. So Simulink will be more appropriate there.
Suppose I am using USRC, in that case, I think it has better option. Simulink has better option for because it has better connection.
Yeah, if you're working with streaming data, yeah, very often I think Simulink will be the better platform than MATLAB. But yeah, but you can do it using MATLAB as well. There is not really any sort of limitation there. Let me just stop sharing for a bit. Just a second. So yeah, I think you can go ahead and generate a bunch of waveforms here, and so to those who are asking, you could go ahead and generate like look at the doc as well. So please utilize this to kind of generate data. So so one way is to synthesize it and again to record it, but what sort of model you build again is dependent on that. So the idea is if you want to look at, say, applying machine learning versus deep learning, you would have to look at trade-offs. One trade-off between machine learning and deep learning is the domain knowledge itself. So if you're so as machine learning requires feature extraction is best done when you know about your own domain, right? Because you know what features will be appropriate, right? So if you the other bit is the data set size. So machine learning can work with a small data set because we know very well what features we are working with. But deep learning would require a lot of data to be generated. Okay. So to understand what technique, either machine learning or deep learning works best for your application, you can look at you can look at considering these two things. Okay. There are other intermediate steps as well. You could go ahead and generate, say, time frequency maps or do a bunch of pre-processing and look at applying deep learning. There are also other approaches to generating features themselves. So if you are using something called wavelet scattering, you can generate a bunch of features which you can then apply to either your machine learning model or to your deep learning model. So, so it is not that you have to resort to either deep learning to deep learning always, but think about these sort of uh, uh, trade-offs between what you want to do as well. Okay, great. So if there are any questions, just we'll come back to those as well. But let's look at the second step in here. Okay, AI-driven system design. All right. So in this case, we'll look at modeling an AI system. So specifically, we'll look at doing generating a deep neural network. Okay. Now, when looking at these steps, we could start off with a bunch of machine learning models, or a bunch of deep learning models, or you could look at reinforcement learning and so on and so forth. Okay. So there are a whole lot of algorithms which are already pre-built, and you can modify these as per your application. Right? If you are working with uh, with, uh, with a specific example, with deep learning in particular, you can use a bunch of pre-built deep learning models, as well as there are a whole lot of reference examples to work with. Okay, so these reference examples are very good starting points for you to begin your work and then proceed to the rest of it. Okay, so let's look at this. At this point, what I'll do is uh, just showcase a bunch of these, and then you can go ahead and try these out yourself. Okay. So just give me one moment. So now, where do I find these? Okay, so when you open up the MATLAB documentation, so if I just open MATLAB documentation, go to help, so this will open up the documentation. And on this side, if I just search for AI for wireless, okay, this will open up a bunch of results. Okay, and in the first one is something that I'm interested in. So AI for wireless. If I just open this up, you can see a whole lot of examples that are there here. So how do I do channel state information feedback with autoencoders, or how do I train reinforcement learning agents for beam selection? So there are a whole bunch of examples which are there for deep neural networks for wireless. Okay, so this is a really great starting point for you to work with when working on any particular problem, right? So what we'll do now is maybe look at one of these examples, specifically say something like modulation classification, and then we'll see how we can go ahead and implement that itself. Okay. So just give me one moment to open that up, and I'll share that with you as well, so you can try that at your end. Okay. Just a second. So So what I'll do is look at what I'll do is I'll look at sharing a bunch of these. So uh, so maybe what you can do is you can look at opening this page up and open this particular live script. Okay. Modulation classification with deep learning. All right. So if I open this particular live script, and let me open this up here as well.
We have R2028.
Praful,
AI is
Okay.
hello Praful.
Yes, go ahead.
Here participants are asking whether this is only limited to R2021, R22.
B. It is
Oh.
we have eight.
We have A.
2028.
Okay. Can you just check if this is available?
Sir, that's what I'm asking. Is it only applicable to R2022B?
No, it should be available in. I'm not sure if it is available in 2020 releases, but it should be there in 20. So this is 20. You are working with R2020A, is that it?
Yeah.
Okay. All right. So let us try a workaround. Let me just go ahead and. So. So let me just go ahead and look at one bit here. So yeah. Let me. So you are working with R2020. So let me just. See which examples are there. So 2020A or 2020B? Can you just very quickly clarify? 2020A, was it?
2022A. It is 2022A. The first one.
Sure. Sure. Yeah. So
The 2022.
okay. So 2022A, right? Yeah. So if you go to the 2022A documentation, so maybe just open up. So let me just highlight a few things. So just observe for now. I'm accessing the documentation on the web, but you might have the documentation installed on your end itself. Okay. So just open up the documentation. Go to the communications toolbox on the left. Okay. All right. And here there would be a section here called deep learning in wireless systems. Yes. Okay. So has everyone been able to navigate to here? So go to the documentation home. Go to the communications toolbox. Click on communications toolbox on the left hand side. Okay. And again, this will open up on the left hand side. Okay. So deep learning in wireless systems, is it there? Has everyone been able to open it? Yeah.
Yes, sir.
Okay. So everyone has been able to open it, right? So what I want you to look at is the first example here, modulation classification with deep learning. Yeah. So can you clarify if you are able to open the modulation classification with deep learning example? Is this clear? The modulation classification with deep learning. What you can do is you can simply open the doc and just search for modulation classification. So if you just search for modulation classification, that should be the first example which pops up.
Yeah. Now everyone can open. Thank you.
Okay. Yeah. So once you do that, right? Once you open this up, there will be an open live script option here. So you can just go ahead and open live script. So that will open up the example itself. Okay. So just open up the live script and then let's just observe me for a little while, and then you can go ahead and try this out on your own. All right. So let's just take maybe a minute to open it, and then let's go ahead and try that out. So has everyone been able to complete it? Sure. Okay. So yeah. move ahead. So just observe the screen for a little while now. Okay. What I'll do is I'll go over the example, and then we'll go over some details here. Okay. And then you can go ahead and maybe explore the example yourself, and we can have a small discussion after that. Okay. So essentially, in this particular example, you can see this is a live script which has some text, some code itself. Okay. So in this case, our objective is to essentially train a deep neural network, in this case, a convolutional neural network, to identify different modulation types. So which will involve 8 digital and 3 analog modulation types. Okay. So how can we go ahead and do that? So in this case, we are defining these categories. So these are our categories which we have defined. So 11 of them. So 3 plus 5, 8 plus 3, 11 in total. And following that, what we are doing is we are simply going ahead and generating a bunch of waveforms. Okay. So in this case, what the neural network is taking on is 1024 channel impaired samples, and it is predicting the modulation of each frame. Okay. So I hope that is clear for everyone. So what is being taken as input? These are 1024 samples. Okay. So it's essentially a vector that it's taking in, and these are channel impaired samples. So there are transmission effects which are already sort of accounted for. So there would be fading, any offsets which are introduced during transmission. Those are already accounted for here. Okay. So in this next section, a bunch of so all of these are sort of generated, and these are sort of used to get the frames as well. So in the section 1, we are just sort of loading a train network, and in this particular section, we are just looking at what the networks themselves are, what the data itself looks like. So we are generating some what the data itself looks like based on some parameters like SNR and offset and center and center frequency and so on and so on. Yeah. So the data generation bit, I think you've already looked at with the waveform generator app, but you are also well conversant with sort of how to kind of create data yourselves. But now let's look at how you can go ahead and create deep neural networks. Okay. So in this case, I have a network which I simply loaded, and this is a 28 layer network which can go ahead and do classification. So let me just go ahead and talk a little bit about that. Okay. So yeah. So I would just request some attention here before you go and look at the examples themselves, because this might be where many of the things, some details might be missed. So deep neural networks are essentially and how many people here have done a ANN course? So I know many of you haven't done a machine learning course, but anyone who has done a artificial neural networks course?
Yes, sir.
If you could just, yeah.
Yes, sir.
Okay. So how many of these are there in the classroom? Maybe anyone who has done an ANN course? Around.
How many?
ANN course किसने किया है?
2-3 students, sir. How many? 1,
Only 2, 3?
2, 3. Any more? 3 students.
Sure. Okay, sure. So let's okay. Let's look at what ANNs are, and then we'll look at that particular example and what that CNN or convolutional neural network itself looks like. Okay, so neural networks are nothing but, you can think of them as a bunch of a combination of neurons. Okay, so neurons are arranged in different layers. Okay, so and what they take in as input is numeric data. So in this numeric data can be our signal samples, it can be your pixel information or so on. It will process that data through a bunch of hidden layers, intermediate layers, and then it will, at the output, it will give you, and there will be an output layer. Okay, so so each of these neurons is nothing but you're simply performing some linear algebra at each node in this neuron. Okay, in this network, each node, each of these white circles is a single neuron. Okay, and at each neuron, you are simply doing a very basic linear algebra. You are doing, you're multiplying the incoming input with a weight, and you're adding some bias to it. Okay, so it is nothing but, if you think about it, a filter of sorts, where you are multiplying with some coefficients, which are the weights, and adding some coefficients, which are the biases. Okay, and this output is then propagated to the next layer, and so on and so forth. Okay, so so what neural networks essentially do is, if you remember the feature space, right? So we had that x and y axis with a bunch of features. So they are essentially looking to take your input data and mapping it to a feature space where it is sort of separable. So if you think about it, so if you think about the neural network itself, so what it is doing is, it is sort of, say you had a bunch of data. So there is some feature 1 and there is a feature 2 here. Okay? So you have a bunch of data here, so belonging to different classes. In our case, these classes would be the different modulation types. Right? So what we would end up doing is, the neural network is essentially trying to taking in these feature values, or taking in some sort of inputs, and trying to map these sort of inputs to a higher dimensional space where this is sort of separable. Okay. Now these are not F1 and F2. These are some, maybe let me put in HF1 and HF2. Okay. So the neural network is sort of using computation. It is mapping these same inputs to a space where it is separable. And now I can easily create a decision boundary between these two classes and categorize them. All right. So neural networks are nothing but doing that. Okay. So what is done during training these neural networks is, we identify what are weights and bias, what are weight and bias values for different layers, and we work with those. Okay. So in this case, let's look at the neural network itself and look at how it works. Okay. So what I want you to do is just observe for a while, and then you can go ahead and try this out yourself. So I'll run just the first part of this example, just the first 5 lines of this example, by clicking on this blue bar over here. So what this does is, it loads a trained network in the workspace for me. So once I sort of see that, so there is a trained network here. Okay. Now, this is an already existing network, but let's look at how you can define these networks from scratch. Okay. So I go to the app section. I go to the drop down, and this time I'm, instead of the signal processing and communication, I'm looking at the machine learning and deep learning section. Okay. Inside the machine learning and deep learning section, there might be a bunch of apps. I want to focus on something called Deep Network Designer. Okay. So if I just type in Deep Network Designer, so it might come up here. So let me just go ahead and open this app up. Okay. So Deep Network Designer is the starting point for the second step that you have to perform. So that is creating a deep neural network. Okay. So while this opens, we will do two things in Deep Network Designer. We'll look at this train network itself, and we'll also look at creating a network from scratch. Okay. So let's look at this. Okay. So again, deep network designers just opened up. So in our case, if I look at the trained neural network itself, so there are a bunch of, if I look at that in the variable, so if I look at that in the workspace, so there would be so if I look at that in the workspace, so it says it's a 28x1 layer. So if I go back to my presentation, so deep neural networks have different layers. In this case, this neural network has 28 layers, including the input and output. Now, what are these layers themselves? If I click on this, so all of these layers open up. So first is the image input layer, a convolutional layer, something called batch normalization, ReLU, pooling, and so on and so forth. Okay. So these are a bunch of layers which are there. Okay. Now, if you look at these, what you can do now that Deep Network Designer has opened up, you can create a network from scratch or import one from the workspace. Okay. So I'll not import the one from workspace for now. I'll just create a blank neural network. Okay. And then you can go ahead and work with this. You can also import a bunch of existing neural networks. So there are a bunch of neural networks which you can go ahead and open. All right. And in case other researchers have put out networks in other frameworks, so there are different machine learning frameworks such as TensorFlow, PyTorch, and so on. If other researchers, if you are reading research papers where researchers have put out networks in those frameworks, you can import them into MATLAB as well. Okay. So for now, let me go ahead and create a blank neural network. All right. So this is a blank canvas where you can go ahead and import neural networks and build your neural networks. So in case your work, so you can see there is a layer library here, and this essentially opens up into a bunch of different types of layers. All right. So there is something like input layers, there are convolutional layers, sequence layers, activation layers, normalization layers, and pooling and other different types. Okay. So in our case, if your inputs are typically signals, you would take in a sequence input layer. Okay. And you could go ahead and simply drop that. Okay. If your so this is if your inputs are sequences, if your inputs are signals. However, if your inputs are features, okay, if your inputs are feature values, which you are computing, you can go ahead and look at importing feature layers. Okay. Now, very often, deep neural networks for images, we have very good deep neural networks which work with images. So one instance, so very often what ends up happening is we convert this signal representation into an image using a spectrogram. Okay. And the spectrogram itself is taken in as image input. Is that clear? Like, so essentially deep neural networks for images are very well defined, and there are a lot of neural networks available for classification. So what we end up doing is we very often convert 1D signals into images and then work with those. Okay. So in that case, we can simply go ahead and import image input layers. Okay. Since we are working with images, we'll go ahead and look at convolutional layers after that, and simply connect these two up. And then there are a bunch of other layers which we can sort of add after. So there's something called ReLU. And in our case, we could look at something like softmax, a classification layer, and maybe a polygon. Okay. So what you can do here is you can simply connect these up. Okay. And each layer has a bunch of parameters which you can go ahead and define on the side. Okay. And then you could simply go ahead and export this network to the workspace or generate code for this network. Okay. So if I generate code, again, it will generate a live script in a similar fashion, where you can go ahead and look at like some code which was used to create this network. So there are image inputs, there are convolutional layers, ReLU, fully connected, softmax, and classification layers. Okay. Now, so this is one way to kind of go ahead and do this. Okay. The other way, let me just go ahead and import the existing network from the workspace. So I'll just go ahead and import it. Okay. So in this case, yes. Sure. Yeah. Please observe for now, and then you can go ahead and try this out on your own. So just observe for now. Don't try to replicate it at this point. I'm sorry? Sure. So do one thing. For now, just observe. Okay. Don't try to replicate. Just observe. Okay. So open up the Deep Network Designer. Okay. Once you open that up, look at importing the network from the workspace, and you just import the train network, okay, which was already there in the workspace. All right. So what I'll do, so don't follow along now. Just observe for now, and then I'll go with a few details, and then you can go ahead and understand. So essentially, if you look at this train network, it takes in an image input. The input size itself is 1 × 1024,2. It takes in some convolutional. There are some convolutional layers. some batch normalization layers, some value layers, some max pooling layers, and then again the same thing starts all over again. There is a second convolutional layer, batch normalization layer, value and max pooling layer, and then a third one. Okay, so so some patterns, a fourth one, a fifth one, and then finally some average pooling, a fully connected softmax, and classification. Okay, so if you think about this, it's essentially the same sort of module. So these four things: a convolutional layer, a batch normalization layer, a ReLU, and a max pooling layer, repeated again and again. All right, that's what makes up the deep neural network. Okay, so now what does this do? You remember I had drawn something like this itself. So what the neural network is trying to do is it is taking in some input data and trying to map this to some sort of output where it is separable, right? So what is happening in these convolutional layers and batch normalization and value layers is it is essentially taking in this input. The first set of these layers is sort of trying to do one operation where it is looking at high level features. Okay, so think of it as if you're taking in a 1024 size input, maybe you're looking at computing averages in that entire window in this layer. So broad level features for the entire window will be computed by these layers. Okay, the later layers, like the second set or the third or fourth sets, will look at finer level features. So these can be maybe average values within that particular, within smaller windows. Okay, so what your neural network is trying to do is going from these input to finer and finer level features all over, and finally towards the end you will typically see classification layers, classification neural networks end in three layers, which is a fully connected, a softmax, and an output layer. Okay, so this will be the same very often for classification networks. So these three layers are typical. All right. So what I want you to look at is maybe just open this up, open the trained layer up. Okay, look at all of the parameters. Okay, if you want to learn what each layer does, you can go ahead and look at specific help on the layer properties. Or if you just want help in general, you could go ahead and look at opening this particular help window and read more about the deep network designer and a bunch of examples here. Okay, so for now, just open the network up, examine the image input layer, look at just one batch of this, and look at the final layers. So fully connected, softmax, and output layers. Okay. And just observe what is happening at each of these, and then maybe just try to replicate one of them. Okay. So maybe a 6-layer network. So where you are looking at image input, CNN1, batch normalization 1, value 1, max pooling 1, and followed by these three. Okay, so I can go ahead and copy these, and I can go ahead and copy the first 5. These to each other. Okay. So what I want you to build is simply this neural network. Okay. Just copy some of these layers and build it up. And then let's talk a little bit more on this. Is it clear? Okay. Just open Deep Network Designer, open the existing network, and see how you can go ahead and build these up. All right. So let's just take 5 minutes. Okay. In case I'm here, in case you want to kind of just ask just anything, then let's go ahead and do that. Okay. Please feel free to voice out.
Show that Hindu.
So have you been able to kind of open the deep network designer and explore the existing network? So have you been able to do that? So maybe a yes or a no. So have you been able to open Deep Network Designer and explore the network from the workspace, which was there in the example?
Sir, we are not able to load the first train.
Okay. So if you already have the example open, you can simply run the first 5 lines. So there would be a blue bar which appears here. So you could simply run that first section and don't run the entire bit, just run the first section. So if you run the entire bit, it might just take too long. Anyone who has been able to open up Deep Network Designer and thought of being able to explore the networks themselves? Yeah. So so essentially, let us maybe then we can go ahead and run it. Okay. So just observe here for again a while. You can go ahead and try that out yourself in a little while. Okay. So so again, the objective is to just introduce you to the entire workflow, because what you will be doing is completely different. Like you will be working on your own examples. So even if you are not able to run this at this moment itself, don't worry, I'll leave resources which you can go ahead and learn in more detail this entire month. Okay, but for now, I just want to kind of make sure that you understand what is happening. Okay, so so just observe this for now. Okay, so just look back at what I'm sharing for now, and I'll again leave resources which you can go ahead and do in detail. You will not learn this in one day, obviously. You will need to kind of again go over a bunch of things too. So let's look at the examples. Then let me walk you through the example very quickly, and then let's talk a little bit. I'll share some resources. Okay. So in the first 5 lines, I'm just looking at. I've just defined a bunch of categorical categories for which are the modulation types which I want to classify. Right. And in the next section, I'm just going ahead and generating a bunch of signals for my classification. Okay. So in this case, I'm just looking at generating frames. So you have in line 60, you are looking at generating signals. So how many samples there are per symbol, how many samples there are per frame is again something that you are going to define. And then how many symbols there are per frame is again a computation which you need to do and look at what are sample rates and center frequencies. Now you can add different sort of in channel impairments, so like fading effects and so on, of clock offsets and so on. So essentially, all of these are something that you can go ahead and do. Right? So a lot of the example itself is just simply going ahead and doing what you already do as folks working on wireless communications. All right. So in this case, what we are doing is nothing but creating this data, okay, and creating these data frames, and sort of associating it with a bunch of labels, which are the different modulation types. Okay. So if I look at this data itself, where it is stored, so all of this is essentially generated and stored here, like if I let me just open this up. So if you look at the data itself, so where all of this is stored is just here. Okay. So there are MAT files which I have generated, and all of these MAT files are just different sorts of modulation schemes, and I've created a whole bunch of them. Okay, so if I look at how many total files, so there are around 2,200 files in all. All right. So this is something till now the machine learning part hasn't even come, right? So this is just we have generated a bunch of files with just what you already do. Okay. And this will take up a large bunch of your time when looking at machine learning workflows as well. This data preparation takes up a major chunk of your time, and it is the idea is to spend a lot of time here to understand what you are trying to do. Okay. Now, if I just look at how these signals themselves behave, so these are some of the plots themselves. So the real and imaginary plots are plotted here. Okay, so you have your real and imaginary values in blue and red, okay, for the signal itself. All right. Now, what we end up doing, as I said before, is a lot of convolutional neural networks have been trained on image models. Okay, so they have been trained to do image classification. So what we end up doing is we end up taking these signals and converting them to images. So we take these image inputs and convert them into spectrograms. Okay. Now this is simply a function which we have written to do that, but inside that there is nothing but a very small piece of code to just create a spectrogram. So inside the spectrogram itself, there's nothing but this is the main function. So we are taking in a signal frame, applying a Kaiser window to it, and just generating a spectrogram. Okay, the rest all is just a for loop, reading the file, and so on and so forth. You don't have to worry about that aspect. So this is how we generated spectrograms from this, and these are just a set of samples. Okay. Now, so any questions till this point of the explanation? Like any questions on this aspect? Is it clear why how we generated signals and why we converted them to spectrograms? Yeah. No questions? Everything clear? Now let's look at the machine learning bit itself. Okay, and I'll talk a little bit about this, and then I'll also share some resource which you can go over and try to learn this yourself. Okay, so what we end up doing is we end up using something called now there are 2200 files, right? In some cases you may end up generating even more, like 10,000 files and so on and so forth. So very often you can't load all of this into memory, right? So this is again somewhere where many of the researchers get stuck. So people end up trying to put everything in memory and trying to train their model. So that is not how things work. So you use something called data stores. Okay, so data stores are nothing but pointers, okay, which you can go ahead and utilize. So pointers, if from your C++ programming, are essentially indicators, right? So you use data stores. You give your directory where you had saved all those samples as input, okay, and then what data stores do is it will automatically help you split your data into training and testing. Okay, so some data will be used to train a machine learning model or a deep learning model. The remaining data will be used to test the machine learning model. Okay, and then you can also perform a bunch of other operations on it, such as give it directly as input to the deep neural network and so on. Okay, so remember, whenever you have to work with a large amount of files, you don't have to use for loops to read it into MATLAB, especially when you are doing machine learning. You use something called data stores. Okay. Now, details of what a signal data store are, again, you can look up in the documentation, but just remember the keyword data store. Okay. Now, there are different types of data stores. There are image data stores, there are signal data stores, and you can also define your own custom data stores if you're sort of giving inputs as specific things. Okay. Now, what I'm taking it on is I've defined a signal data store. I've given the data directory as input to it, and I'm storing it as a variable called frame ds. Now, if I look into what is there in frame ds itself, you'll see that it is a signal data store with these properties. It has files, around 3 plus 2197 more. So all the 2200 files are somehow referenced here. Okay. And if I read the first file, it will read this file 16 quam001.mat. If I read the third file, it will go ahead and give me that. Okay. So you use data stores to essentially identify which is the first point and then go ahead and learn this. Okay. Now, if you can go ahead and look at splitting this data store into training, validation, and testing as well. So essentially, if you define some sort of training, validation, and test samples, so in this case, we have defined it as use 80% of the data for training, 10% for validating whether your training is correct or not, and 10% for testing. Okay, so think of it as what you teach during a class is your training. Okay, and you spend a large amount of time doing that, a large number of examples doing that. Your validation is something like quizzes during the class, so you just ask impromptu questions. Okay, and your test samples are essentially what appear on, say, an end term exam or a mid-sem exam. Okay, so when trying to train a machine learning model, again, things happen in a similar fashion. So you present data to the machine learning model in this fashion. A large amount of data is used to tune the weights and bias the parameters of the network. You use some amount of data to keep checking in between whether the network is functioning well or not. And then you use a small amount to test at the very end. Okay, so you get 3 different types of accuracies as well: your training accuracy, your validation accuracy, and your test accuracy. The objective would be to have the test accuracy as high as possible. Okay, so training accuracy will be high, like accuracy should be high, but the test accuracy is what matters. Okay, now following that, it's simply sort of reading a bunch of data into memory and trying to train this. Now, if I look at training this itself, what this will do is essentially go ahead and look at define a bunch of training options. Okay, and look at training. So you generated data, you used data stores to load data, you used some things to split data into different parts, and then the other major function or what you want to remember is train network. And what train network does is essentially you give inputs to it, which is your training frames, your labels, and a bunch of options. Okay. Now, so this will open up the training progress chart. So where you are essentially going to sort of highlight how you'll train this. Now, any questions on this bit? And any questions on data stores? Any questions on training, validation, testing, and the train network? Like, just I know we covered it at a very high level. You still don't understand what is happening in the background, but any questions broadly on this?
this data store, actually, whenever you want to execute some program, the data should be in a workspace where they can execute. So how you are saying if you use for loop or data stores are much better. But ultimately, we are reading the data into workspace. What is the difference between these two approaches?
Sure. Yeah. Perfect question, I think. And so that is where you have to kind of think about, that is where the difference comes. So your workspace, your workspace has limited memory, right? And some of you who are working on very large simulations might have run into memory errors, right? So you cannot store each and everything on workspace, right? In workspace. Very often what you will end up doing is you'll save this to files, right? You'll end up saving, say, some instances to files, either a MAT file or a CSV file or an Excel file of some sort, right? Now, what happens in machine learning and deep learning is you need access to a large amount of data, right? So it is not immediately used. So if you load all of the data into memory, very often it is not possible to do that because the data itself is gigabytes and gigabytes. So in many cases it might run into say 20 gigabytes or so on and so forth. So or even if it is lesser, we don't need all of the data available immediately in one go. Very often when training a network, we only need one example at one point, right? One data point at one point. Right? So what data stores do is allow you to just define where the data is located, okay, and load the relevant data point at runtime. Okay, so it will just load what is needed when it is required. Okay, so that's the difference.
After that, it will clear that once it is loaded and its work is over. After that, it will clear that and
Clear
go
it.
to the next one. Okay.
Yes, exactly. So that way your memory is sort of, if you're working on an 8 gigabyte RAM computer or a 16 gigabyte RAM computer, so how would it fit a 20 gigabyte training data which is there? It wouldn't, right? So yeah.
Yes.
So it would load it at runtime and clear that. Okay, sure. Any other questions? Yeah. So one more thing that data stores allow is the splitting of data. So instead of you going and looking at splitting data manually, so where you say that I want to take out of the 2200 files which were there, I want to take the first 2000 files and use it for training. Okay. So instead of you defining that manually, you can go ahead and there are a bunch of functions such are available to, so for you to split things randomly and do that. Okay. So and that is again very useful because remember you have 11 classes. So 11 classes split across 2200 files. So how do you kind of select an appropriate number of files from each class? Okay. All right. Now, yeah. So I realize a lot of you, like again, a lot of this was very new. A bunch of this might not again be very clear. So what I want you to do is, again, since we are at the very end of this session, I'll cover a few more slides. But again, how do you go ahead and try this out at a slower pace and by yourself is, if you look at the MATLAB window itself, you see this Learn MATLAB option here. Okay, so if you just simply click on that, it will open up the browser and it will go to something called matlabacademy.mathworks.com. Okay. So what? So this is essentially an online portal where you can go ahead and do a bunch of courses for using MATLAB for various other things. Okay. So since many of you are very new to machine learning, what I would say is look at the getting started section of this. Okay. There are a bunch of 15 courses which are available to everyone for free. Okay. So these 15 courses are available for everyone for free, regardless of whether you have a license, you don't have a license, and so on and so forth. Okay. So in this case, what you can go ahead and do is look at the MATLAB on-ramp, look at image and signal processing on-ramps. There's an on-ramp on wireless communications, as well as on-ramps on machine learning, deep learning, and reinforcement learning. Okay. So what these on-ramps are, so let me just open up the deep learning on-ramp itself. What these on-ramps are, so these on-ramps are essentially roughly 2 to 2.5 hours or 3-hour courses, which introduce this topic to you, as well as how to go about this, learning this in a step-by-step fashion. Okay. So again, if many of these might not be directly related to wireless, but it will give you a fair idea of how to do things in MATLAB. So in this case, for example, the deep learning on-ramp, you look at how to use pre-trained networks, how to manage collections of data. So in our case, we were looking at signal data. In this case, how to manage collections of image data, how to perform something called transfer learning, and do that. Okay. If you look at the machine learning on-ramp, instead, you look at how to import and pre-process data, how to compute features, and how to do classification models. Okay. So if I just open up part of this course, this is not a video course. You can go ahead and you'll have to end up coding some parts of it based on a small problem given to you. Okay. So in this case, let me just open this up. And these again are refreshed. These courses are refreshed every 6 months or so, or every 6 months to a year. So what you can end up doing is you can go ahead and look at doing these courses again and again just to try things out. So for example, here, this is what the course itself looks like. So your task is to read the data stored in a text file into a variable. Okay. And until you complete the task here and submit it, and whether it's only when it is correct, will it move to the next task. So the task, some background is provided. So in this case, reading data from a spreadsheet or a text file uses something called read table. So I can simply copy this. My data is in j.txt. So what I'll do is I'll just type in j.txt, and I'll have to read it into the variable letter. So I'll just go ahead and do that. Now if I just do it letter 1 and submit it, and it will give me an error saying that this should be something different. Yeah, so you can try this course out. For some reason, like I think it's taking too much time for me. Maybe because I'm connected to the internet while and sharing video while this is running. But you can go ahead and try this out. At the end of each course, what you will get is a certificate. This is an official certificate from the MathWorks training services. So these are the same courses which are available to industry as well. So all of these courses which you see here are the same courses which are available to industry users in, say, an Ericsson or a Qualcomm, where they are using MATLAB and Simulink to sort of create these algorithms and for their devices. Okay. Now, is this like, how many of you have seen these courses before? How many of you have tried these on ramps? Yeah.
Sir, are these courses available on crack version also, or we need a authentic version?
So these, yeah. So these courses are available via the browser, and these are available via to anyone. So these 15 courses are available to anyone without a license as well. So you can go ahead and try this out. Okay, and all of these run on the browser itself, do not really require a license to run this. There are additional courses which are longer. So there are courses for, say, 16 hours and longer courses on machine learning, which are further advanced. But these require a license. But you know, you can skip, focus on the basic courses for now. Okay, before looking at the advanced ones. Okay, I hope that answers your questions. Any other question?
Students attendance.
Any other questions? One. Okay, sure. So I'll just take maybe 10 more minutes and quickly wrap up. Is that okay?
Yes.
Sure. So sure. So so the first thing, again, so we looked at a bunch of we'll look at one example. We looked at deep network designer. Now, very often in deep neural networks, when trying out deep neural networks, you will have to try out multiple deep learning experiments. You'll have to try out various deep neural networks with different configurations, different parameter values, and so on. And you'll have to run all of these. So in that case, you will have to run multiple deep learning experiments together. Okay, so to identify which is the best network which does your job. Okay, so in that case, there are a bunch of other apps which are available. Essentially called, there's an app called Experiment Manager, which can design and run multiple deep learning experiments and give you the best one, which helps do that. Okay. Now, once you have designed and identified which is the best experiment, you could also go ahead and look at quantizing the deep neural network. Okay, so quantizing it as in essentially limiting the weights and biases to be represented in a particular fixed point format, so that it can be implemented on a hardware. Okay. Now again, this is useful because very often your deep neural network will have to perform some real-time task on sitting on some hardware, right? So especially in the wireless communication space. So you'll have to look at that aspect as well. You can go ahead and import TensorFlow models, PyTorch models directly into MATLAB. If there are models built in any other frameworks, you can again import it into MATLAB through something called Open Neural Network Exchange. You can also export learning models built into MATLAB into other frameworks. You could go ahead and do that. To train deep learning, again, you could go ahead and look at accelerating So if you look at system design simulation and also the deployment aspect of it, once you have trained your deep learning model, you can go ahead and generate code and have the deep learning model run on an ARM device or a CPU. So you can generate C++ code. You can generate CUDA code for your NVIDIA GPUs. And you can go ahead and generate HDL code, either Verilog or VHDL code, for running on FPGAs or SoCs. Okay. So again, someone had asked earlier whether it would be possible to generate code from MATLAB or whether we would need to do it in Simulink. You can generate code from both. So there is not really any sort of limitation there. Okay. You can also look at using MATLAB with other languages. So essentially, you can call C++ directly from MATLAB or execute Python functions or scripts directly from MATLAB. And you can also call MATLAB from other languages. So you can go ahead and call MATLAB, do some processing in MATLAB, pass the results back to your base processing language. Okay. If you look at the final bit of that particular example itself, so if you look at the final bit of this particular example, so the last part of it involves testing with SDRs. So essentially, you can go ahead and test with either USRPs or ADLM Pluto radios. You can directly import data from there and test out what is the sort of modulation which is happening. So you could go ahead and transmit things as well as read inputs and then go ahead and try this out. Okay. So test out the performance of the trained network using this over-the-air signal capture. Okay. Finally, if you finally, if you want to look at more detail, what I would suggest is you visit this particular page on the MathWorks website. So if you go to the MathWorks web page, and if you just search for something like deep learning, or if you just scroll down here, so there are a bunch of things available, and you can go ahead and look at solutions and deep learning. So inside deep learning, there are a bunch of pages for deep learning applications. So whether you are trying out deep learning for wireless, deep learning for signal processing, for radar, LiDAR, and so on, you could go ahead and look at that particular application. So if I just look at deep learning for wireless, so this particular page is something that you can use as a go-to for your work on wireless. Okay. So this is a really useful page you can look at. There are a bunch of examples built in here. And these are again from spectrum sensing to device identification, PPD, beam management, to localization and transceiver design. So also there are a bunch of videos on how you can do this in MATLAB. So there might be some videos which are just 30 minutes long. There are others too, which are almost an hour long and so on. And take one particular example, run through it from beginning to end, and which will give you a little more detail into how things are. Okay. So please go ahead and visit this page definitely and try things out. Okay. So just go ahead and again, remember what the 4 steps. So you could go ahead and synthesize data, do channel compliant, do standard compliant waveform generation, to your deep learning, and then also look at connecting to over the air, connecting to test equipment, measurement and test equipment to look at over the air testing. Okay. So if you are looking at teaching any of these, look at there are a bunch of courseware resources available for teaching digital communications or introductory communications using SDRs. These are ready-made courseware which are available with MATLAB code, some presentation equipment, some presentation and so on, which you can go ahead and utilize as well. Please go ahead, look at the on-ramps, utilize the wireless communications on-ramp and these courseware materials to do more. If you want to find where the courseware materials are, you can simply look at the academia page and look at the teaching section and look at the courseware. So if you look at all the courseware, there are a bunch of courseware for wireless communications which are available. So some of the on-ramps, yes, but also some of the examples available here. Okay. Yeah. So that's primarily, in addition to that, there are a bunch of data science and other courses available on MATLAB Academy as well. Please go ahead and utilize those. And finally, look over the examples and videos to do more. So that's primarily it from the two of us. Please feel free to get in touch with us, and we'll be happy to sort of talk more with you on your research problems and your particular specific work as well. Yeah. So I'm happy to sort of stay back, take any questions. I'm so sorry we couldn't do this in person. We really wanted to sort of look at it in person, but unfortunately we couldn't do that. So this was the next best thing. So thanks for staying back and sort of taking us back. So in case you want our emails, go ahead and do this. So let me just share these. Yeah. So this is just our emails. Let me just share again. So these are our emails. Please feel free to sort of get in touch. We'll be happy to sort of discuss more and do go over the examples and look at this. So in case you get stuck anywhere, please feel free to just email us. I think that would be the best way to get in touch. And yeah. Thanks again for all the time. I'm happy to take any questions now. Maybe we could stay back. I'm happy to stay back till 5:30. Yeah, please feel free. Thanks.
Thank you, sir. Thank you, sir.
Yeah.
Those courses are not opening, sir. Just 2 hours introductory courses are not opening.
We have to enroll actually.
They are not opening. So you can. So you can go ahead, try this out. Very often they are also dependent on the internet connection, but try this out. They should definitely open. So yeah, so they're working for me. Please try this out on your own. Okay. Any other? Do try out. We keep on adding courses as well. So do keep checking this particular website for new courses as well. So for example, we introduced the wireless communications on-ramp just in January of this year, and something like the power electronics on-ramp just 2 months ago. So we keep on adding a lot of courses here. So please utilize these to the maximum extent possible. Any other questions? None?
No question.
Okay, sure. All right then. Thanks a lot for your time. Yeah. Take care. Good luck for the rest of the